Okay, so let me check something real quick. And if I go here, all right, so it's 6 o'clock. People are starting to taper off. So I will more than likely start locking out. I'll probably be a little lax for these first few sessions, but I'll probably start locking out the attendance at the 15-minute mark. So I've been kind of avoiding it, but 6 o'clock and I only got 2 people here. So and those are going to count as unexcused absences. So, whenever possible, you want to let your brothers know, hey, you might want to be here a little bit early because it's going to start locking it out. You get locked out, then the whole unexcused absences thing is going to start to rack up. And that means you can get booted, you won't get your money back, and more than likely you won't be able to get back in. You're going to waste your time and money, which is what I don't really want to do, but I need people to be here. I feel like asking you guys to just show up is the bare minimum, right? I don't make you come on, I don't make you talk, you're in a non-proctored environment. So at a minimum, I need you guys to show up on time whenever possible. And then I just really at a minimum, I just need you to show up and submit your assignments, and I don't make a big deal about it. But if I notice that people aren't showing up or they're coming in late, too many people start coming in late, then I was like, okay, I'll shift gears. So anyway, hope everyone enjoyed your spring break, right? I did. It didn't feel like spring break to me, but I still enjoyed myself. I always, find some way to enjoy myself. This question came in not too long before the start of class, so I want to kind of take a moment to explore it. Let me see. So we'll take a moment here. Now, I don't know if that's the right answer. I just want to copy and paste. Are you going to let me paste? Sometimes you be acting funny. That's not what I want. Share. Copy. Okay, so you're not going to let me paste. Let's go here.
Excuse me, Professor, I have a question.
Is this Mr. Simpson?
No, it's all right, Mr. Jones.
Go ahead.
Regarding the assignments, is there I understand are the quizzes able to be done like no matter what the circumstances are?
I'm listening.
Or can you skip around depending on
your audio cut out, you have to say it again.
Sorry, I said, can you skip around the quizzes, or do you have to do them linear, like in chronological order? Because I realized that some of them have prerequisites, but like let's say you wanted to, like you had quizzes that you didn't previously do. Is that still something that you can get points for?
As long as you can access it, then yeah, whatever you can access, you're welcome to do it. If it requires a prerequisite, then you have to do the prerequisite.
Okay, sounds good. Thank you, Professor.
Where is that thing, man? Let's see. It's not those. It must be. It's one of these. What is this? All right. So I'll do another set of announcements after we, closer to the 15-minute mark, just to try to get as many people in as possible. So again, this question came in. Let me see if I can pull some details about this guy. Done. We can delete. This question comes from section 2.5. Where is the question ID? Well, this is okay, there it is. It comes from section 2.5, question 35. Let me go like this. So this was submitted by a student as a starter class, maybe an hour or so before the start of class. I was like, okay, I'll use that to open up today's lecture. So let me see, how much must you invest now Okay, where is my pen? ¿Dónde está aquí? All right. So how much money must you invest now at 4.1% interest compounded continuously in order to have 10,000 at the end of 6 years? Okay. So this sounds like, I think this is this course. Let me see. Yeah. So the formula here is compound interest, continuous compound interest. So I call it the PERT formula. We can call it. Let's go 5. So the future amount equals P e to the RT. I may or may not have introduced it that way. I may have introduced it as, you may also have seen it as like AFT. These are just labels. You just kind of got to get the right nomenclature. E to the KT. It's the same thing. Same thing, just different labels, right? But my point of reference is the green on the left, but they mean the same thing. Okay, so let's fill in what we have. It says how much should you invest in? So that means we're trying to solve for P. So I'll put P here. E is a function in the calculator. Now, if it's 4.1%, whenever we use percents, we have to convert them to a decimal. So the percent symbol, you can replace it as times 1 over 100. So in other words, move the decimal to the left 2 spaces, 0.041. It says at the end of 6 years, so we're going to say that number times 6, and we want to finish with $10,000. All right, $10,000, right? So we have P times some number equals 10,000. So then, long story short, the amount we need to invest in starting now is just going to be 10,000 divided by whatever that number is. All right, E to the 0.041 times 6. So now, when you're doing these calculations, if you crunch a number along the way, you have to write out the long decimal, right? If you crunch a number along the way and you round early, it's going to make the earlier that you round, the more skewed your final answer is going to be, and the likelihood of you getting it correct is going to go further and further down. So you have to do one of two things: either keep it exact like this and only round at the very end, or if you crunch numbers along the way, you have to write out the long decimal every time until you get to the very end, and then you only round at the very end. Okay. So, and this is one of those concepts that students struggle with through all my classes: college algebra, pre-calc, calculus, all of them. Because for whatever reason, it's usually like laziness. I mean, that's only human nature, but that's why we're here, to try to override those natural inclinations. Energy follows the path of least resistance, but like as a divine being, we have that ability to override that natural factor and make the unnatural natural and make the natural unnatural, if that makes sense. Anyway, so let me break out my trusty dusty rusty. I can just go like this. Close all these tabs. All right, I can hear people trickling in. Like I said, I'll make an announcement in about like 7 minutes or so. Okay, this looks good. How can I get this to work? Okay. Reload. Come on, reload and refresh. Okay. All right, so then 10,000, 1, 2, 3, divided by E to the power of 0.041 times 6. Okay. Let me see what you had over here. Let me see if that's correct. Enter 78. Yeah, so okay. With the question that was submitted, the number was different, even in like the ones position. So to me, that says that more than likely you rounded along the way. So again, if you crunch numbers, you have to write out the long decimal every time and only round at the very end, right? So when you did the E, you get this long decimal, you got to write out all 8 or 12 digits, however long the decimal is. You got to write out the long decimal every time until the very end. Okay, and so you can try it again. You might be able to use this result because it should be 2 decimal places. Nearest cent, yeah. So I got approximately 78.19 and 22 cents. Yeah. So either this, if that doesn't work, then try 23. You know, either one of those should work for this one. Okay. All right. Let me think. Okay, so again, yeah, we're back from spring break. We only have two sections. I think when we left off, we got caught up. I'm under the impression we did. I know we had to do a little bit of like finagling. I know we lost a day, but that's why we have our pre-recorded lectures. So whenever we have hiccups, we can we can recover in that fashion. Let me include a screenshot of this. Come on. My device is taking its sweet time. Come on. Oh no. All right, all right. Can we reset it somehow? Okay, that's fine. That's what I wanted. That's fine. I mean, we don't need all that. We can go like that. Just come on. So that way you have a copy of that. And so I'm just including this in today's notes. I'll minimize that. And let's kind of go on to the next page. Okay, we'll start here. That's fine. Matter of fact, let me duplicate and clear. Yeah, that looks good. Okay. Yeah, so we had spring break. You know, I think we had to like kind of adjust the schedule a little bit, but I'm under the impression that we got through at least 3-6, and I know we didn't go through everything together because we, you know, I think we lost a day. I know we were having some trouble with Zoom. Eventually, I was able to connect with the IT, so we got that should be fixed by now because like somehow the system got reset, and I somehow got back onto like a free plan. That's why I kept cutting off. So then they were like, so they just upgraded me to the full version, so that way we can actually hold class. So we shouldn't have any issue with that. So you know, we have been having some technical difficulties, but we got through it. So the goal for today is really just section 3.7, elasticity of demand. Okay, so we're just going to kind of hop into it. And again, the recommendation, you know, you don't have to wait for us to do this live. My recommendation is use my pre-recorded lectures to get ahead. Idealistically, you want to be ahead of me, so that way when we do it live, in an ideal world, this would be a review for you, right? So that's, you know, because the stuff I'm going to say live, all of that's in my pre-recorded lectures. I'm just doing it this way, just kind of as a courtesy, really. A few objectives here. Let me hop here. Zoom, come on, right there. I want to join. That is correct. That's fine. Don't connect and join. Stay as the participant. Cool. Okay. Okay, good. We got more people trickling in. I'll make an announcement in a few more minutes. I'll give people a little bit more time to get in.
Everything in black, right?
Thank you. Okay. So some objectives here. Find the elasticity of a demand function. Find the maximum of a total revenue function. Characterize demand in terms of elasticity. Okay. So the elasticity of demand is given as a function of price X. Elasticity of demand. Let me see something. Give me just a moment. Okay, the total revenue increases at those X values for which the elasticity. Okay, so we're going to come back to that formula in just a moment. I just want to kind of clear up the elasticity of demand. So the total revenue is increasing at those X values for which the elasticity is less than 1. So we're going to go revisit that formula in just a moment. But when the elasticity of demand is less than 1, the total revenue is increasing at those values for X for which the elasticity is less than 1. The total revenue is decreasing at those X values for which the elasticity is greater than 1. And the total revenue is maximized at the value or values of X for which the elasticity is equal to 1. Okay. So the elasticity of demand E is given as a function of the price X by this guy here. The elasticity is negative X times D prime over D. Okay. And then we have these theorems or properties, what the elasticity is telling us. Okay. And so notice that the total revenue or the total money generated is maximized when the elasticity is equal to 1. The revenue is increasing when the elasticity is less than 1. The total revenue is decreasing when the elasticity is greater than 1. Okay. So in economics, we have elasticity of demand for video game rentals. For whatever reason, I just across my mind's eye, I got this image of like Blockbuster, and I was like, man, Blockbuster used to be the place. Like when I was younger, that's kind of revealing my age a bit, but like it was Blockbuster, right? Because you have either movies and video games. Sometimes I rent systems, and it was like the pace was totally different. It was a totally different experience. Now we stream everything. Everything is download. Right, everybody has their own phone, so we have screens like right in front of our face. I don't know if you've seen the series Black Mirror. If you have not seen that series, I highly recommend it. It's a little bit like really, really jarring in that first episode, but the remaining episodes are like they're interesting, and it's so interesting because this is like a plausible near future scenarios. It's like they're making the screen smaller and smaller and closer to our face, so we have more and more distractions, which means we're more easily controlled. And like some of the concepts they get in there are like really interesting. So how we went from like Blockbuster when I was younger to like now everything is like streamed and downloaded. It's just like a totally different experience, and everybody has their own personal device. Again, screens closer and closer to their face. Black Mirror explores realms where the screens are inside of your head, right? Like it's like a lens or like Neuralink and stuff like that. So I was like, oh man, and like some of the scenarios are really really trippy. Okay, so in this example, the demand for video game rentals at Clicks Video Games is given by this our demand function, all right, where Q is the number of video games rented per day at X dollars per rental. Find the elasticity of demand as a function of X. Is the time. Let me see. Okay. Let me finish reading this and I'll do my announcement. So find the elasticity at X equals 2 and X equals 5. Interpret the meaning of these values of the elasticity. Find the value of X for which the elasticity equals 1. And then what is the significance of this price? Let me see something. Okay, so we got a few more people. All right. So usually in the past, what I would do is at the 15-minute mark, I would lock out access to our sessions, right? So 15 minutes, if you're not in by the 15-minute mark, I lock it out, then you can't get in. That counts as unexcused absences. I think we're allowed maybe 2. I usually give students 3. Definitely by the time I see 4 unexcused absences, then you can be booted and not be able to get back in and waste your time and money, right? That's what I try to avoid. And I'm only saying this because like when we started class, we got a good amount more. I do need to I probably will go through and if I notice that people have like 4 or more unexcused absences, I might submit their name to be like purged. If you know that you have 4 or more unexcused absences, maybe at the end of class, just try to stop me and say, hey, I think I might be one of those students that have 4 or more. I do intend to finish. Like, let me know that you intend to finish so I can put you on a list of like, do not purge. Because if you get purged, and just again, get my attention at the end of class, but like if you get purged, it can be difficult. You may or may not be able to get back in. And so like I try to avoid that because if you get booted, it's just a headache that you don't want to have to deal with. Again, the simple thing is just show up about at least 5 minutes early and zen out. I don't, I try to make it like as light as possible, and then submit your assignments promptly. So yeah, if you think you have 4 or more unexcused absences, just to end the class, just get my attention so that I can add you to my do not purge list, so that I can try to minimize collateral damage, right? Because again, you don't want to be on the list. For unexcused absence. And you can check, I'm basically using Blackboard to log attendance. So if you see like 4 or more unexcused absences there, then, that's what I'm going to be using to kind of go through that. Okay. So part B asks, find the elasticity when X is 2 and when X is 5. Interpret the meaning of these values of the elasticity. C, find the value of X for which the elasticity equals 1, and then what is the significance of this price? Okay, so we kind of need our formula. Where is my pen? Here it is. I'm going to try to do it off the dome. Again, these formulas, you don't really need to commit these to memory. You just need to know how to use them. Elasticity of demand, I think it was like negative X D prime over D, something like that, where D was the demand function. Was that our price? I think D prime is our demand function. Yeah. Okay. Okay, that's fine. So we're asked to find the elasticity. Okay, let me see if I can give myself some space. Let's see the options. So this is, I needed to be slide 10. Let's copy right here and paste. And I guess I'll just go back and forth. Okay, let me just pull this. We'll reference that. Okay, we need this, a copy of this demand function. So our Q is our D of X, 120 minus 20X. Okay. Find the elasticity of demand. Okay. Paste. Okay. All right, so for part A, our elasticity of demand, negative X. So let's go ahead and find D prime. Looks like it's just negative 20. Okay. So negative X times negative 20 over 120 minus 20X. Okay. So we have a double negative at play, so this is positive. Okay. Looks like we can factor out a 20 from everything. Right? If we factor out 20, this is gone, this is gone, this, what is this? Turns into a 6. So it looks like we have 6 minus X under X. Okay, so that's what we get for our elasticity of demand. So then part B, find the elasticity when X is 2 and 5 and interpret the meanings. So basically it's asking us to find E of 2. It's also asking us to find E of 5 and then interpret the meaning. Okay, so E of 2 is going to be what? 6 minus 2 under 2. So 2 over 4, which is what, a half. Notice that's less than 1. So when the elasticity is less than 1, the total revenue is increasing. All right, so we haven't maximized our revenue, right? So we might be able to sell it for more, right? So we can say that the total revenue is increasing. Okay. And then the elasticity of demand when X is 5. So I think if the first one is like if we're selling it for $2 each. Second one is if we sell it for $5 each. Okay, let's see what happens. So that's going to be what? 6 minus 5 under 5, which is 5, which is what? Greater than 1. So in the second part, the elasticity of demand is larger than 1. So the total revenue should be decreasing. So we might have overpriced. We might have sold it, it might be selling it too high, right? Something like that. You can say the total revenue is decreasing. Okay. Let's see what C is asking. Find the value for which the elasticity equal to 1, and then what is significance. So again, when the elasticity is equal to 1, that means the total revenue is maximized. So that's probably ideal. We need, okay, so X over 6 minus X. Let's duplicate. Okay, let me clear out. Let me see. So we can do, I kind of need that. I'm going to get rid of this. That, like that, get rid of that, like that. Delete. Okay. And this is C. We want to find what value of X makes it. We want to solve for E of X equal to 1. So that's going to maximize our total revenue. So then on the left, we're going to have what? 6 minus X under X equals 1. Okay. And we need to solve this. Okay. I'm going to subtract 1 from both sides. So we're going to have 6 minus X under X minus 1 in the following form. So I'm really subtracting 1, but I'm going to do it in the form of 6 minus X over 6 minus x. Something divided by itself is 1 equals 0. I'll keep working over here. Now we can distribute a negative into the top. Looks like we're going to have x plus x minus 6. So look, it's going to be 2x minus 6 over 6 minus x equals 0. And this is going to be 0 when the numerator is 0. What when x is 3? All right, if we set the numerator to 0 and solve, looks like when x is 3. Notice that 3 was between the two original values we had for part B. We had when x was 2 and when x was 5. X was 2, the total revenue was increasing. When x was 5, the total revenue was decreasing. So it would stand to reason that the price that would maximize the total revenue would be somewhere in between. Notice that 3 is between 2 and 5, right? So our claim is that the total revenue is going to be maximized when we sell each rental for $3. $3 per rental. Okay, so that's when we did it ourselves. Let's kind of compare it to the way that let's see what the textbook did in comparison. Okay, I think we got that elasticity of demand, right? Negative x times d prime over d. So ultimately they got x over 6 minus x, the same thing that we got. All right, I'm being kind of lax. Let me see. Okay, so I think we kind of have who we're gonna have. I'll be chill, for right now. But again, if I notice that people are trickling in, like I'll try to just focus on the 15-minute mark. But like right now, for instance, we have like I think it's like 12 of you guys here, something like that. But if I notice that people are coming in later and later, or like in the last few minutes, then I'll probably start locking out the access at the 15-minute mark. I don't know why I'm stuttering so much today. I'm trying to talk too fast. Anywho, but yeah, we got this elasticity of demand, but I want to give you guys a heads up so that you can like adjust. I don't want to just like spring it on you. Okay, so we got the same elasticity. So then for part B, when x was 2, we got a half. When x is 2, the elasticity is less than 1. Therefore, a small percentage increase in price will cause an even smaller percentage decrease. Since the demand is inelastic, raising the price of each rental by a small amount will increase the total revenue, right? Yeah. Let's see. Small percentage of price will cause an even smaller percentage decrease in the quantity demanded. Okay. So I mean, I think what the analysis that we had before was fine. And then in the second part of B, the elasticity was greater than 1. So a small percentage increase in price will cause a larger percentage decrease in the demand. Since the demand is elastic, raising the price of each rental by a small amount will decrease the total revenue. Okay. So then if we want to find what price to set it to maximize the total revenue, we set it equal to 1. We got x equals 3. This is the price that will result in unit elasticity. At $3 per rental, Clicks Video Games will maximize its total revenue. The demand, if we sell each rental at $3 a piece, is going to be 60 rentals a day, and the revenue is going to be $180 generated per day. Okay. So based on the price, that'll tell us the demand and then how much money we can generate per day. That's really interesting. Well, that wasn't too bad. We're almost done with this section. We only got like a few more slides left here. And I was really trying to save 3-8 for Wednesday. Quick check I usually leave as an exercise for you all. We might hop into the homework. Yeah, we're done. I guess it was just the one. That wasn't too terribly bad. Okay, wait a minute. We're missing some slides. We are missing a slide. No, we're not. For whatever reason, they just weren't showing up. Attendance is grayed out. Okay, I can see that. Yeah, you can send me an email, right? I just got at least one email. So like, yeah. If you check your attendance in like Blackboard, if you notice that you have 4 or more unexcused absences and you intend to stay, just let me know so that I don't purge you. So like it's kind of like a no show, no call. If you have 4 or more unexcused absences and I don't hear from you, there's a good chance that you could be booted from the course, right? And then that's a whole headache. Sometimes students can get back in, oftentimes they can't. So if you know you might be in jeopardy of getting purged, just go ahead and shoot me an email. Like, check your attendance. If you have 4 more unexcused absences, shoot me an email. Say, hey, I do have 4 more unexcused absences. I do intend to finish. Please do not purge me, right? And hopefully, that should work. That's going to be much better than not doing anything at all, right? If you fall into that category. Okay. But I did just get one student to message me via email, so that will suffice. Okay. So yeah, we have the slides over there. I don't know why that wasn't working, but that's fine. So how many slides do we have then? If that's the case, that was kind of throwing me off. Okay, so this is the last one. So we'll go ahead and work with this. So elasticity of demand. We have Wayne's Honey Farm sells honey-based moisturizing cream for $12 a jar. At this price, okay, I think we got to do some scratch. At this price, it sells for 14,500 jars per month. To see if the price is too high or low, Wayne's Honey Farm raises the price to $18 per jar. At this price, it sells this many per month. Use the exponential demand function, this one, okay, to find the following: the elasticity of demand. Find the price at which Wayne's Honey Farm should sell its jars of moisturizing cream for a demand to have unit elasticity. Also give the results in total monthly revenue. Okay, we got this. We got this. Let's see. I'm going to copy of this guy. So I just want to copy. Hopefully it'll allow me to paste. There we go. It's not allowing me to paste. Let me try one more time. Okay. It's not working. Let me try one more time. Copy. Copy. Right here. Paste. Okay. Okay, so we got this demand function. Okay. Let me get a copy of this guy. So basically find the elasticity of demand and then find what is it called? The unit elasticity. Okay. So all I need is this guy here. Wait a minute. I'm not even really sure if we need that other stuff or not. But I'm going to start with this demand function. I'll take it from here. Use this as a reference. So it might be a little bit small, but again, it's just for reference. Come on. Yeah, if this technology, if it's not one thing, it's something else. Like, come on. It's not behaving. Let me see if this works. This one, there we go. There we go. There we go. Yeah, it's just so temperamental. Okay, anyway. Okay, so as we did just a moment ago, right? The elasticity of demand should be what? Negative x times d prime over d. Okay. So we got our demand function. Let's go ahead and find d prime. And d prime of x, we got, okay, so it's basically the derivative of e. The derivative of e is itself times the derivative of the power. So that's going to be this 26,380.746 times e to the negative 0.04987 times x. Then we need to say times the derivative of the power. The derivative of the power there is going to be this negative 0.04987, right? So basically, original function times that coefficient from the power. That's going to be our d prime. I'm going to kind of leave it like this. So then if we want to calculate our E of x, our elasticity of demand, that's going to be a negative x times this guy. So it looks like it's a double negative. So I'm just going to go ahead and make it positive. We're going to have this number, 4987, times this 26,380.746 times e to the negative 0.04987x. Let me clean it up because I know how beautiful my handwriting can be. That's going to be a little bit better, I guess. Okay. Then we need to say what over the original function. So we're going to say divided by the original, which is this guy, 380.746 e to the 0.04987x. Are these guys going to cancel each other out? It looks like all of this cancels all of this. We have something divided by itself, right? So it looks like our elasticity of demand, I think this is what part A. Looks like it's just this guy here, the 0.044987 times x. That looks like our elasticity of demand. So then we want to find our unit elasticity. In other words, what value of x is going to make this equal to 1? I think I got enough space here. I'm going to go ahead and do part B right here. So if we set that equal to 1, ultimately x is going to be, our unit elasticity is going to occur if we say 1 divided by that coefficient, provided we did our calculations proper, right? So it looks like, okay, let's calculate, let's crunch that number right here. Okay, so let's do 1 divided by 0.04987. Okay, $20, $12. Okay, that's fine. It's looking like we're getting about $20.05. So we say this is approximately $20.05 per jar is going to be unit elasticity. Okay, let's see how do we do. Right, that's just us kind of like following the breadcrumbs. We took our formula for unit elasticity. We calculated our d prime, our derivative of our demand function. Then we did negative x times d prime over d. We had a lot of things to cancel. We had a double, we had a double negative at play. So it became positive. We got that elasticity. And we got a unit elasticity of about $20. That's a reasonable result. So, we're going to go with it. Okay. Oh, and then let me see. It also asks us some more information. And then also give the resulting total monthly revenue. So if we sell ours at $20.05 per jar, that we can plug that into our demand function to see how many. Let me see. Let's plug it into our demand function. It's a little bit jumbled. So what I'll do, I'm going to go to my y equals. I'm going to put my 26,380.746 times e to the power of this negative 0.0498 times x, okay? And I want to evaluate this function when x is that $20 that we calculated just a moment ago. So I'm going to call on that function. I want to evaluate that function when x is $20.05. So our claim is that it's going to be a demand of like, it's either 970 or 971. Let's just say we'll sell about approximately 971 units at $20. So then the total monthly revenue is approximately. I know it's a little bit out of order. I'll just separate it. Like I just do the remainder of B in another color. I'll use this color. So then I'll just call this B sub 2. So then the total monthly revenue so it should be the $20.05 times after we plugged in, we got 970.84. So I'm going to say times 971. So we should be able to sell about 971 jars in a month at $20.05 based on this demand function. So we just say that 971 times that 2005. It might be thrown off a little bit because we were rounding a little bit early. It's almost $20,000 in a month in revenue. All right. So we get approximately, so the total revenue for the month, 19,465.42. Okay, let's see, how do we do? Okay. What's our time? 6:40. We still got about 30 minutes. Okay. So let's look at what the book did. To find the elasticity of demand, 4987, I think we got that exact same result. Let me highlight it. So we got that result right here with a better highlight. This color. Okay. So that's a good omen. So we're good there. So everything we did there was fine. And then to find the price, $20.05. That's Wayne's Honey Farm should sell its jars for $20.05 per jar. That would maximize the revenue. The monthly revenue generated 194,600 approximately. So they rounded, but I think we got the same thing. Oh, wait a minute. Oh, we did something wrong. Command function, I plugged it in there. 20. Okay, maybe I typed it in wrong. Let me see here. So that's demand. If that were, let me see. If we said 971 times 2005. I got like 20,000. Okay, what's the frequency of this? Let me see. Because the only part that's a little bit off. I know we kind of did the same thing. I'm just trying to get to the bottom of why our numbers are so different. We plugged it in. Maybe let me see. Maybe I typed it in wrong. Let me go check another location. Let me check this. That needs to be a 05. That did not do it. 194. Okay, let me see. What are we missing? Okay, let me check here. Oh, yep, there it is right there. I tried 380. I'm missing my 0. That's why. Insert a 0. So you got to be careful when you're typing 746 e to the negative. Okay, let's quit. And so basically, we need to do the 20.05 times that function evaluated when x is 20.05. Yeah, we were just missing the 0 in our calculation. Okay, so we had the right idea. We just, the execution was a little off. Right here. Let's get rid of this. Come on. Let's go this way. So that should be 9706. Okay, right here. And I'll show the correction because that error came because we typed it in the calculator wrong. This should have been approximately 9706. Okay. And then I'll fix this one as well. We had 194,604 and what, 65 cents? That's fine. So again, our error came just because we missed that 0. We typed it in the calculator wrong. But aside from that, everything else was fine. Okay. Let me see. So yeah, I think we're good there. Not too terribly bad. Okay. Let me just go through the summary real quick, and we'll take some time to go through some of the corresponding homework, and I'll let you out. We'll probably, let me see, at least 15 more minutes. We still got a solid 30, but if we can hang out for at least 15 more minutes, then we're good. I find a demand function. For a demand function, Q equals D of X, where X is in dollars, the elasticity of demand is going to be negative X times D prime over D. The demand is inelastic when our elasticity of demand is less than 1. If the demand is inelastic, then a small increase in price, the revenue increases. So I think we said earlier that when the elasticity of demand is less than 1, the total revenue is increasing. The demand is elastic when the elasticity of demand is larger than 1. If the demand is elastic, then with a small increase in price, the revenue decreases. So again, if the elasticity of demand is larger than 1, the total revenue is decreasing. So a small increase in price will decrease the total revenue, right? So then unit elasticity occurs when the elasticity of demand is equal to 1. Then that's when the revenue is going to be maximized. Let me see. Okay, so let me see here. Not too bad. Let me kind of check. I want to check something real quick. I want to see, because we might be able to just go ahead and do 3.8. Let me just see how many slides are here. Single page. Because if we can do it today, then we can take Wednesday as 25. I am tempted to do this today, and we'll just either we can get ahead or review on Wednesday. So, let's. I kind of want to go ahead and go into the next section. So we're gonna go ahead and do that. Okay. So this is the last section for chapter 3. Let's go ahead and finish this, and then I'll give you a little bit of disclaimer there. Let me check. Okay, so yeah, I think that the guys that are here. The numbers haven't really changed. So I gotta track down what's happening with these other gentlemen, like, because there's a good amount of you guys not here. So obviously it doesn't pertain to you all because you're here. But I have noticed that, like, okay, I need to track these guys down. So again, like, if you're here, and again, I can't stress this enough, you might want to check your attendance on Blackboard. If you notice that you have like 4 or more unexcused absences, just send me an email like promptly so I can see it, or catch me at the end of class so I can make a note so that I don't submit your name to be purged. But a lot of guys have been like a no show no call, and so I'm gonna go check those attendances. If I see 4 or more, I'm gonna say, hey, I haven't seen these guys. I don't know where they are. And usually what the admins do, they boot them, and then sometimes the student's able to get back, and sometimes they aren't. So you just don't want to be in that boat if you can avoid it. Okay, so the last section for chapter 3. Oh, I like this. Oh, section 3.8, implicit differentiation and logarithmic differentiation, right? I'm going to give my own summary here, right? So this whole time, right, these 3 chapters, we've been exploring the derivative, right? The summary, the simplest way I can summarize the derivative is the slope of the tangent line at a point. And we explore, like, we introduce the concept with, like, starting with a secant line, 2 points crossing a curve, and then as the second point gets closer to the first. We also introduce the derivative with the limit definition of the difference quotient. Then we explore some differentiation techniques that were like pretty much shortcuts. And then we explore like some applications of derivatives, this, that, and the other, right? So with this whole discussion, we've been doing like y in terms of x, right? So with implicit differentiation, what it is like, what if you have the functions so far have just been one function in terms of one variable. What if you have a function that's in terms of more than one variable? How would you explore the derivative there? That's what implicit differentiation is. So you might have like some function that's a function of 2 or 3 variables. How do we find a derivative, right? That's what we're going to be exploring here. So it's, it takes a little bit of mental gymnastics, a little bit, but once you get it, it's kind of fun. Like, it's not too terribly bad. So objectives. 1, differentiate implicitly, and 2, use logarithmic differentiation to find derivatives of certain functions. Okay, let's see here. So to differentiate implicitly, differentiate both sides of the equation with respect to x, or whatever variable you're differentiating with respect to. Let me pause right there. So when we take the derivative with respect to a variable, like if we're taking the derivative with respect to x, the other variables, we treat them like a constant. right? So you might see some functions are going to have more than one variable. When whatever variable we're taking the derivative with respect to, the other variables we just treat them like a number, like a constant, right? That's the mental gymnastics of the whole thing. So once you kind of get used to focusing on the variable that you're differentiating with respect to, again, the trick is the other variables you just treat them like a number, okay? And we're going to see it in action. Apply the rules of differentiation as necessary. Anytime an expression involving y is differentiated, dy by dx will be a factor in the result. Isolate all terms of dy by dx as a factor on one side of the equation, factor out dy by dx, divide both sides of the equation to isolate dy by dx. Let me see. Okay, so there are two techniques that we're going to explore. I think that the way that the book does it, like say we're taking a derivative with respect to x, whenever we take the derivative of y, we're gonna put the symbol dy by dx. Whenever we take the derivative of x, you just take the derivative like normal. So that's, again, let me repeat the way the book does it. The way I'm under the impression that the way the book does it, if we're taking the derivative with respect to x, whenever we take the derivative of y, we're going to put the symbol dy by dx. Everything else is like normal. Okay. The other technique that I like to do, whenever I take the derivative of y, I put dy. Whenever I take the derivative of x, I put dx. And then at the end, I'm going to have like dy and dx all throughout the function. I'm going to use algebra. I'm going to use algebra to get dy by dx on the left, everything else on the right. So I'll probably showcase both of those techniques. Okay. And then you just pick whichever one you resonate more with. So for this example, find dy by dx using implicit differentiation, and then find the slope of the tangent line to the curve when at the point 0, 3. Okay. So this is a function based on two variables. Let me do the way the book does it first. So for instance, again, whenever we take the derivative of y, we're going to put dy by dx. Otherwise, everything else stays like normal, usual rules of differentiation. So for instance, that first term, y to the third, right? So that derivative is going to be what? 3y squared dy by dx. Okay. Now plus, this middle expression here, we have to use what? The product rule. First times the derivative of the second plus the second times the derivative of the first. Okay. So the first is this guy. The derivative of the second is this guy. Again, whenever we take the derivative of y, we're going to put dy by dx. So that's the first times the derivative of the second plus the second times the derivative of the first is just going to be 2x. Right? So notice I just did that derivative like normal. And then lastly, the derivative of x to the 4 is 4x cubed. The derivative of 27, that's a constant, so that's going to be 0. Okay. So now our goal is any term that has a dy by dx, we're going to keep it on the left. If it does not have dy by dx, it goes to the right. Okay. And I'm going to go ahead and factor out my dy by dx. Okay. So that's this guy, 3y squared. That's this guy. I'm going to rewrite it as 5x squared y to the 4. I've already factored out my dy. And on the right, I move these last two to the right. So I'm going to have my 4x cubed minus 2xy to the 5th. Okay. So now we have dy times this expression equals the other expression. So then if we isolate the dy by dx, it's just going to be the right over the left, essentially. All right. So then ultimately we get dy by dx equals, the bottom is what? 3y squared plus 5x squared y to the 4 under 4x cubed minus 2xy to the 5th. And that's the showcase of implicit differentiation. So again, we essentially took the derivative like normal. And with the way the book does it, their technique is whenever we took the derivative of y, we put dy by dx. I haven't showcased the other technique just yet. Let me check and see if this is correct. I will come back to the second part. 4x cubed, 2xy to the 5th, 3y squared, 5x. Yeah, we got it, right? And then part B, find the slope. So we have our derivative when x is 0 and y is 3. Okay, so I'll take some notes here. So when x is 0, looks like everything collapses to 0. Because if x is 0, this goes to 0, this goes to 0, this goes to 0, and this is not 0. Like that last term is not 0. So essentially, we're going to have 0 over a number, which is 0. So then it looks like the slope of the tangent line at the point 0, 3 is ultimately going to be 0. So let me see, at 0, 3, dy by dx equals 0. Okay, let's see, how do we do? Yeah, right. Again, 0 over some number, we got 0. Okay, so again, with this technique or this concept, like for these purposes while we're together, just try to absorb it. Don't try to read every little minutia detail. Just try to get the main takeaway. We're kind of covering two different techniques. We've only done one of the techniques. The first technique is you take the derivative like normal. All the usual rules apply. It's just whenever you take the derivative of y, you put dy by dx. Right? Otherwise, do everything like normal. At the end, you use algebra. You want to isolate your dy by dx, everything else on the right, and then you're good to go. Okay? So that's the way the book does it. Let me see if I can showcase mine. For this demand differential implicitly define dp by dx. Okay. I don't know if that's going to be easier. Now, sometimes the way the book does it is easier. I don't know if mine is going to be easier here or not. I'm gonna try the way I like to do it here and see if I can get it to work. If not, I'll just default to the way the book does it. So this one wants to take the derivative of p with respect to x. I'm going to showcase the way that I like to do it. So the way that I like to do it is whenever I take the derivative of a variable, I'm going to put d that variable, right? When I take the derivative of x, I'm going to put dx. When I take the derivative of p, I'm going to put dp, right? Okay. And then I'm going to use algebra to get dp by dx, okay? So if we're going to take the derivative here, the derivative of x is just going to be dx, all right? It's just going to be 1 dx, okay? Now on the right, it looks like we got to use the chain rule. So then the 1/2 comes down. We're going to have this 200 minus p cubed to the power of a negative 1/2 times the derivative of the inside function is going to be this negative 3p squared. We took the derivative of p, so we need to put dp. So if we want, we want dp by dx. Before I use my algebra, let me kind of get rid of this negative power, this negative exponent. So I'm just going to kind of rewrite this. That moves to the denominator, so we're going to have 2 times the square root of 200 minus p cubed. That's in the denominator. On top, it looks like we have this negative 3p squared dp. I'm going to leave the dp over here. So if I want dp by dx, I can divide both sides by dx and multiply by the reciprocal. Right? In other words, divide both sides by that fraction. Long story short, dp by dx should equal the reciprocal of that guy, negative 2 times the square root of 200 minus p cubed, like that, over 3p squared. Okay. So we got a result. Let's I'm just going to compare it to my prepared notes. Okay, I think we got the same thing. 2 times the square root of 200 minus p cubed over 3p squared, and the negative can move to the top and bottom and be the same thing. Okay. So now if you notice the way the book does it, again, they took the derivative, let me see. When they took the derivative of p, they put the dp by dx, and then they just use algebra to isolate the dp by dx. So we've officially showcased two different ways of doing implicit differentiation. We got a solid 10 or 15, about 15 minutes, but I'll probably do another 10. I want to try to keep going through this. Given this guy, find dy by dx. Okay. So I'm gonna do a random. If the number ends up being odd, I'll do it the way the book does it. If it's even, I'll do it the way that I do. Hey Google, give me a random number between 1 and 100.
Here's a random number, 69.
9 is what, odd? So we'll do it the way the book does it. Okay. Animal dollhouse is coming. I don't know what that means. So the way the book does it, if we're trying to find dy by dx, every time we take the derivative of y, oh, well, it's already isolated, so that should help us a lot. But this looks nasty because it looks like we got to use like the product rule. We got to use like so many different rules. Okay, so this one is less about implicit differentiation and more about all of our differentiation rules in one go, right? So we want to find dy by dx. So the main connector here is that multiplication in the center. So we got to use the product rule. First times the derivative of the second plus the second times the derivative of the first, right? So we might need some space here. So the first is this guy. The derivative of the second, we're going to have that half come down. It's going to be to the power of a negative 1/2 times the derivative of the inside function, negative 15x to the 4. Okay. So that's the first times the derivative of the second. And then we need to say what? Plus the second, which is this guy. Second times the derivative of the first. So we got to use the chain rule. So there's going to be a 3. We got this x to the 4 plus 3x minus 1 squared times the derivative of the inside function, 4x cubed plus 3. Okay. That's really supposed to be on one line, but this is just how it came out. And I think this is fine. Do we have any like terms that we can factor? I want to expand that. Okay, it looks like they both have that x to the 4 plus 3x minus 1. They both have at least 2 of those. Let me see what I'm gonna just piggyback off the text here. Natural log. Why did they do that? Oh, does that make it easier? I totally forgot about that. But I'm trying to think why would they do that? Mm-hmm. Mm-hmm. Hmm. Okay, hang on. I'm gonna come back to that one. Let me see. Okay, so there's that one. Just trying to think of why we do that. I think it just kind of simplifies it. Because where we left off, I think we're still pretty much there though. Give me just a moment. Square root. If we factor that out, do we need to rationalize? Because I know we can get at least 2 of them. Only thing here is how to recognize when to use that technique of taking a natural log. I can't give an explanation as to why we do it, but I just know that that's one of the techniques, right? So it's like when you get something like this, you might try taking the natural log on both sides and then take the derivative and kind of go from there. And it's supposed to be a little bit easier. And sometimes it definitely does make it easier. I just forgot about the technique. I'm just gonna, and just for the sake of time, because I'm kind of rushing a little bit here, I'm gonna piggyback off the prepared notes. So we had this long guy here. Let me see, using logarithmic differentiations. It doesn't say anything. Yeah, it doesn't say anything about it. So using logarithmic differentiation, start by taking the natural log on both sides, right? So from the log rules, right? When we take the log of a product, that's going to be the same as the sum of the logs, right? So if we take the log of a product, we can rewrite that as the sum of 2 logs. Now, you know what? I think what it is that this is just going to be easier to differentiate because we're not going to have to do the product rule and all those multiple rules, right? I feel like this is going to be much easier to differentiate than what we did, right? So again, when we take the log of a product, we can rewrite it as the sum of the logs. Let me see, what else did they do? Okay, they brought the half down. Then okay, so what it did, it kind of got rid of the powers. It pulled those numbers out of the power. Then if we take the derivative from here, the derivative of natural log is what? Dy over y, right? So on the left, we would have dy over y. All of these are going to be du over u, right? You can see it here. Here's du over u. Yeah, that's actually much easier to handle. And again, du or dy over y is essentially dy. Because again, whenever we take the derivative of y, we put our dy by dx. We get something like this. And then I think that's pretty much it, really. They just pulled out a negative, but it's the same result. And then multiply both sides by y. Okay, that is much easier. Okay, so one thing I've noticed, like that technique of taking a natural log on both sides, in the original example, we had these powers, right? That was causing chain rule, like excessive chain rule and stuff like that. So instead of dealing with those powers, like that radical and that 3, again, we took the natural log on both sides that allowed those powers to come down, and it just simplified the expression drastically. It was much easier to work with. I just totally forgot about the technique, right? I started to do it, and then I was like, okay, we got here, but then here we're trying to like do a lot of factoring and this and the other. It gets really sloppy really fast. So I'm going to strike through this because I just, like I said, I just forgot about the technique of taking the natural log. But again, they took the natural log on both sides. If anybody needs to see those details, I can either work it out later. We kind of just went through it. But yeah. But that one, we took the natural log on both sides. Like I said, I just forgot about the technique. Okay. I think, was that it? Okay, let's try this one. Oh, okay. Find the absolute minimum. Yeah, I think we got time. Let's try to go for this one. Okay, so find the absolute minimum value of this from 0 to infinity. So absolute min is going to occur when what? The derivative is 0. So now at first glance, right, if we try to take the derivative, we got x to the power of x. You're like, what? So now that we have in our awareness, hey, try taking the natural log on both sides. That's what we're going to do here. I just like, and I knew it was something that I was like, what am I forgetting? And then I was like, let me glance. I'm glad I didn't like sit there and struggle with it. So let's at least do a showcase on taking the natural log on both sides. So we want to take the derivative here, but again, we have x to the power of x. Got this funky little power thing going on. So we're going to take the natural log on both sides. Okay. So then we got this y equals, we got x to the power of x, and we're going to do the same technique on taking the natural log on both sides. Okay. This allows this power to come down in front. Okay. So now we're going to have what? The natural log of y equals x times the natural log of x, okay? So now when we take the derivative on both sides, on the left we get du by u. In other words, it's going to be dy over dx times 1 over y, all right? This is du over u. But again, when we take the derivative of y, we put dy by dx. And then on the right, we need to do the product rule, right? So the first times the derivative of the second. So the derivative of natural log of x is what? 1 over x. So that's going to essentially be a 1. That's going to be x over x. So the first times the derivative of the second plus the second times the derivative of the first. The derivative of x is just a 1. Okay, so we get this. So then we're getting that our dy by dx equals, multiply both sides by y. So it looks like we're going to have, if that's a 1, x to the power of x plus, here, let's write it like this. X to the power of x times 1 plus the natural log of x. Okay. So then the absolute min should occur when the derivative is 0. So let's set this guy equal to 0 and solve. Okay. So if we have x to the x times 1 plus the natural log of x equals 0, I'm going to go ahead and distribute this guy. We could use the product rule. Yeah, let's use the zero factor property, right? So we have two things that multiply to give us 0. Either this guy equals 0, or this guy equals 0, right? I don't think we have a value of x that's going to make the guy on the left equal to 0, right? So for the left, I'm just going to say like no solution here. But on the right, I think we can get a solution. If we subtract 1, we get what? The natural log of x equals -1. Raise both sides to the power of e to get rid of the natural log. So e to that power, e to that power. And these guys cancel. So then we get x equals e to the power of -1. And then, so that's our critical value. Then we need to we could probably use the second derivative test. Let me see. We would have to find the second derivative though, which I don't really feel like doing. This is our critical value. We just need to confirm that this is the absolute minimum. So we could also choose like a value, x value on the left, x value on the right, and show that the function goes from decreasing to increasing, right? So we need to use the first derivative test. Just for the sake of time, I'm not going to do it because we're pretty much out of time. I'm pretty sure that this is the correct answer. I'll make a note though. Use the first derivative test to verify. Use the first derivative test to verify. All right, but I'm getting this result. And again, I'm just going with it for the sake of time. But like what we would do is like crunch that number, right? We get some decimal. We choose the x on the left. We choose the x on the right, and then show that the original function is going from decreasing to increasing. That means that this would be an absolute min. I mean, we only got one critical value. We could use the second derivative test as well. Okay, but I'm going to go with it. Let me see. Okay, so they took the natural log on both sides. Differentiate implicitly. 1 plus natural log of x. Okay, y times that. Okay, we got that. Okay, so we got to that same point. Set it equal to 0. Since we can ignore the factor x to the power of x since it's never equal to 0. So then 1 plus the natural log of x, e to the -1, which is approximately this decimal. Using the first derivative test, the graph of f is decreasing on the left side of this and increasing on the right. So therefore, this is a relative min. Furthermore, this is the only critical point on this interval. And by the max min principle 2, it must therefore be an absolute minimum, right? Because we only got one critical value. And it's a minimum. So then, it's the absolute minimum as well. So therefore, f of this is going to be that is the absolute min value over this. Okay. It wasn't too terribly bad. Once we had that little trick of taking the natural log on both sides. That was an interesting question because it kind of drew or pulled on like many concepts that we've talked about. But we just officially finished chapter 3. So let me do some like closing remarks, right? So again, I think we kind of got our crew. I know we lost one person, but I was like, that's okay. I'm not gonna make a big deal about that. And again, I'll be kind of like I've noticed that like these past few sessions, it's been about these same students, right? So I think that some other guys have either fallen off or they may have given up. And as gentle as I am, I try to be, and like as much as like unlimited attempts, everybody doesn't make it, guys. Everybody doesn't make it. It's not, I know it seems very unassuming the way I go about it, but I only do that because everybody doesn't make it. Like it's, at a minimum, showing up, submitting, and then, you get unlimited attempts on everything. I try to encourage you to like collaborate. You're in a non-proctored environment. Like it doesn't really get much. But then on my end, I do have to acknowledge life. People are dealing with life, right? People losing loved ones. I've lost students like to just gun stuff, gun violence and this, that, and the other, or just random stuff. So life happens, right? So, I try to be a little bit patient. So with us finishing out chapter 3, it's quote unquote, we've officially finished like our narrative on the derivative. We have our final chapter remaining that we'll probably start next week, probably on Wednesday. We're gonna more than likely we'll just probably use Wednesday as a review session, going through like homework questions and things of that nature. And we'll probably start chapter 4 next week. I don't want to get too far ahead. So chapter 4, the reason we kind of had the pace that we've had up until now is because it's not a calculus course unless you make it through integration, right? So far, what we've been doing up until now, we've been working on the derivative, given a function, how to find the derivative, right? With chapter 4, what we're going to do is, given a derivative, how do we work backwards to get to the original function, right? So that kind of brings everything home, it brings it all together. So that's what we'll probably start next week. Again, we'll probably use this upcoming Wednesday. I might even do something a little bit different. We'll see. But at a minimum, we'll use Wednesday to kind of go through some homework. Are there any burning questions before we go our separate ways, gentlemen? Going once, going twice.
Yes, Professor.
Yeah.
I'm it's Nicholas Ongoma. You told everybody to hit you after class. It's about like the paralysis.
Yeah, just send me an email.
Okay.
Yeah. If anybody, and like try to send it now. If anybody else, if that pertains to anybody, just send me an email right now. It's the best thing.
Okay, I sent you email too, and I also sent you a direct message on Zoom, but I email's probably better.
That's probably a little bit better. Either email or a text, but email is the best because I'm just keep you all together, so that way if I submit these names, I'll know that it's these students here that they want to be sure not to be purged. Yeah, and then just going forward, at a minimum, just try to show up maybe 5 minutes before the start of class, and then you can zen out. I'm not gonna like hound you. I'm not in that boat of like, Mr. So and So, are you there? Are you not there? I'm not doing that anymore. It just makes me crazy. I'm trying to be as chill as possible. So at a minimum, I just need you guys to show up, and with our assignments, keep in mind that we get unlimited attempts. The system is set to take your highest score, and there's an automatic extension built into every assignment. And the only deadline that's a hard deadline is at the end of the semester, right? That Friday, like during the week of finals, that's the hard deadline. So you got at least another about 8 weeks or so to get everything in. Okay. You can collaborate, you can work with the tutors, use my office hours, work together, like it's okay. I just need people to get their attendance and submit their assignments. If there are any other burning questions, we're going to end the session here, gentlemen. Enjoy the rest of your evening, and we'll meet back on Wednesday, same time, same place for the next assignment. Take care, guys. Peace.
Can I talk to you after, Professor?
Yes. Let me stop the stream. Does it need to be private?
No, not really.
Okay. You can go ahead then.
I just need my attendance updated.
What's your last name?
Taylor.
Do you have like?
Yeah, I have like excuses that like basketball season just ended.
I'm sorry.
Yeah, basketball season just ended, and I missed a lot of class.
Oh, basketball. Yeah. Your last name is Taylor?
Yes, sir.
Yeah, because I see those emails. I'll just try to make a note.
Okay.
Yeah, because I know that you all had a lot going on there.
Yeah. Thank you.
Okay. Anybody else? Going once, going twice. Mr. Taylor. Okay. All right, gentlemen. Good luck with everything. You know how to reach me if you need me, and take care. Peace. Okay. Let's see. Here.